Well, thank you for inviting me. I'm a software guy, so I'm learning a whole lot about hardware this week. This is work we did in a European project, the release project, and the paper it comes from was essentially summarized the whole project, which is why almost anyone who made a technical contribution is in the author list, and it appeared in Topless last month. So the slogan, the claim, is that the only way to build a scalable and indeed the only way to build a reliable system is to control state. Shared state is catastrophic. If each component needs to access shared state, then it limits the scale because you get huge amounts of contention on the shared state, or synchronization if you want to change it. And worse still, if you're trying to be reliable and you have a failing computation, it can either screw up the shared state or die while holding locks or capabilities or something, and that just poisons the system. The way actor languages work, and microsystems are just the same thing at a slightly larger scale, microservice architectures. They avoid shared states. You have actors or services that have entirely local state, and they communicate either by messages if you're an actor or through an API if you're a microservice. And you can recover from failures because if one actor dies, you're guaranteed that it hasn't done anything horrible to any of the other actors. So it's like having an operating system process in the programming language. OS processes, you can kill -9 and life is still good. Better still, many of the actor models have something called supervision, where one actor can supervise another actor, detect its failure or slow response, and do something about it. Often kill it and replace itself, replace it, or if it keeps failing, do something else. And indeed, a supervised actor may itself be supervised, and you build a whole tree of these things. Okay, so these microservice architectures are really widely used. Twitter, for example. I'm interested particularly in actor programming languages, and Erlang, for example, has been used to build services like WhatsApp. It's a single Erlang server that ships I forget, is it 7 billion texts every day? It's a huge number. These servers typically run on commodity hardware, and so failures are pretty common. They happen all the time, but the systems keep running. Okay. So we're looking at the Erlang programming language, and yes, the model is great, it inherently scales, but actually the architecture, the virtual machine, dates from, and programming language date from a Unicore era, and it had some inherent scalability limits. And in the project, we look at these at the VM level, at the language level, and the tools level. I'm going to talk only about the language level issue. So the way WhatsApp and these other big servers, Bet365, if you use them, that's an Erlang engine, they use bespoke workarounds. They've got some magic that makes it scale, but they have to spend time building and maintaining those workarounds. So what I'm going to do is I'm going to tell you a bit about how Erlang works. I'll introduce some benchmarks. I'll tell you what we discovered from exploring those, and then I'll tell you about some of the language level improvements we made and some measurements to show that they work. Okay, so Erlang, this is an image of an Erlang system. We have some hardware, that's a blue rectangle. We have virtual machines, also called nodes in the Erlang world. Each node may reside on many cores. Oh, sorry, the hardware has cores, and a VM can use multiple cores. It has a number of processors. Processors are associated with a core through a scheduler, and the virtual machines are connected together, in fact, in a fully meshed network. So here's a bit of Erlang code. You can spawn a function. So you create a process which executes some function called Pong out of some module, and this returns process ID, and then you can use that process ID to send messages to that process. You can do this, by default this happens within the same VM, but you can direct it to some other node or VM, and then you get a PID, and you address that PID, you send it messages irrespective of where it is. Okay? How does the reliability work? Well, Erlang processors are actors. They have private state. Erlang has strong typing. It's dynamic typing, but it's the supervision process where one Erlang process supervises others, and these supervision trees can span multiple nodes. You can supervise a process on a remote node. Now, if you build a distributed system, you often have a process that's providing, it's effectively a server, it's providing some function. If that process dies, the clients of that service need to know how to reconnect to it. So effectively you have a global name registration. So you register a name, Pong server, to be the PID I just created. And then you can send it a message by calling a function called whereIs. So I don't care where this is, find it and send it a message. If the Pong server fails, then its supervisor will simply create a new process and reassociate it with that name, and all the clients can find it. Anyone understand? No? Good. All right, so some of the benchmarks I'm going to use. There's something called an orbit, which is essentially a big transitive closure. It's a slightly fancy version of transitive closure. So you start with a set of values, a set of generating functions, and you generate new values. These are stored in a distributed hash table, so you have a bunch of workers which each generate values and maintain part of the distributed hash table. So it looks quite a lot like a NoSQL DBMS, React or Cassandra. The other one is an ant colony optimization. So this is a machine learning a heuristic way of solving NP-hard problems. You use ants that explore the space randomly. And in fact, we arrange them into multiple colonies. So the ants within the colonies iterate for a while and then periodically send their best solution to a master. The master chooses the best solution from all and feeds that back into all the colonies. In fact, that master, for scalability, this master is a bottleneck, so you could build a tree of submasters to reduce the scaling bottleneck. We build a number of versions of this. So we call this one multi-level. We add reliability. So in the initial version, if a single colony fails, if a single colony fails, the whole system fails. So we add supervision to make it reliable. Okay. Well, the first element in the scalability study was to discover that the fully meshed connection that's produced by distributed Erlang by default works fine. So you have quadratic n squared numbers of connections for n VMs. That's fine up until about 40 VMs, 1600 connections. Once you get to 50, it limits the speed up. So what people like WhatsApp are doing is they're building bespoke networking. They're moving away from that network connection. We also looked at the impact of global commands. So what happens if you interact with global information like registering a new name. So we built a simple peer-to-peer benchmark that compared local commands that you execute in your own VM, commands like spawn that connect two VMs, and global commands that require information to be communicated globally. And unsurprisingly, if you have even a tiny number of global commands, it completely nails your scalability. So this was on a cluster with about 100 machines. They were 8-core machines, but if you have no global commands, it scales beautifully. As soon as you introduce any, crashingly unsurprisingly. Okay, so our idea was to introduce S groups, essentially to partition the network that reduces the number of connections so that within an S group, the VMs are fully connected. You have a fully connected mesh, but S groups don't fully connect. So you introduce individual links between S groups. It also reduces the size of the namespace or the global information. You replicate information only within the S group. When I say partition, it's not a set partition because a node can belong to a number of S groups and you can build arbitrary topology. So we've built rings of S groups, but most of the architectures are tree-shaped. So this is some of the example commands. So you can create a new S group, you can register a name in an S group, etc. Once you do this, so if you partition your nodes in this way and then repeat the benchmark I just showed you with 1% or I think it's 0.01% of global operations, you immediately recover your scalability. They work. There's the semantics, which I don't really have time to show you, and we validated that semantics against the library implementation using something called quick check, which automatically generates thousands of tests. And we found, as usual, mistakes in the specification and in the library. Okay, so now if you're going to use S groups, what do our benchmarks look like? Well, if you remember previously, we just had a fully connected mesh of workers, which looked quite a lot like that. Now we partition, so we have little clumps of workers, and then we more or less introduce a group of gateway nodes called submasters. And if you want to send a message from worker 1 in group 1 to worker 2 in group N, the message is routed through the gateway nodes. And this is what it looks like. So you create an S group called master and give it a name and give it a list of nodes. And then if you succeed, you send messages there. Okay. ACO has a similar structure. So we group the colonies together, and then we have a kind of top-level group for the submasters. Does it work? Short answer is yes. So the most interesting thing to do, I think, is to compare the 2 million curves. So if you're computing orbits containing 2 million elements, the original distributed Erlang is the red curve, where the scalability peaks around 40 nodes. Whereas if you group things, the scalability is the green curve, and it basically continues to scale. Is that it? Sorry. Yeah, okay. Okay, so we've fooled with the Erlang, distributed Erlang model. Have we preserved the reliability mechanisms? Do they still work? So we ran something called Chaos Monkey. Chaos Monkey is a process that runs in every VM, and it randomly kills processes. I think it was Amazon came up with this for testing their cloud services infrastructure. But it's such a useful idea. It's widely used for testing reliability. And it works really, really well. In fact, we can't see any measurable difference in the runtimes because recovering an Erlang process is so quick. These are stateless processes. If you have to recover state, then that may change. Okay. If you look at the impact on scalability of keeping this recovery information, it's really very significant. So as soon as we add recovery information to ACO, our runtimes, our execution times grow hugely. So this is so-called weak scaling. Each time we double the size, the amount of hardware, we double the size of the problem. So you would hope to have a linear relation here, that the execution time remains constant if you solve a problem that's twice as big with twice as much hardware. But it's absolutely not, because we're now having to synchronize the recovery information across 256 hosts on a large cluster. If we keep the recovery information only in the S groups, that's what SR-ACO does, and that's the mauve line here. So the comparable points are the GR-ACO and the SR-ACO. So this is reliable distributed Erlang. This is reliable SD Erlang. So with S groups, here we are maintaining the reliability information only within the S groups, and the performance is much better. In fact, it's better even than the original distributed Erlang implementations, because it has less network traffic. Oh, and that's what this slide is about. So if we measure the amount of network traffic, here the global reliable is the top curve. That's where we have to maintain these global names across all VMs in the system, and the amount of communication required to do that is very large. The original distributed Erlang ML has the next amount of communication. That's because it's maintaining a full mesh of VMs, so it's maintaining all the connections. SR-ACO has fewer connections still, even although it's got global information, and so the amount of communication is least of all. Okay, so this is it. You can wake up now. This is the only slide you need to pay attention for. We studied the language level scalability issues in Erlang and discovered that the two key issues is maintaining a fully connected network of virtual machines and global recovery data. We proposed S groups to partition the network and recovery data, and this is really a systematic way of doing what developers have been doing, Erlang developers have been doing in the background, building home-rolled versions of this stuff. We now provide open source libraries in a systematic way of scaling these systems. And we did some measurements to show that it works. So partitioning the network reduces the network traffic. We haven't messed up the reliability model of distributed Erlang, and maintaining global recovery data. And we can get over the cost of maintaining global recovery data. So we think other folk could maybe use this approach. So vade mecum just means this is a way of tackling the problem. The work's reasonably high impact, so there's about 50,000 downloads of our improved Erlang OTP system every month. Some reflection on the scalability study shows that it's quite possible to build actor models that don't scale well if you get the algorithms wrong. So it isn't a magic formula that just works in all cases. But actually, many of the scalability issues that we saw arise where Erlang steps away from this idea of enforcing isolated state. So there are things called ETS tables where you can have large shared data structures. You make them look like processes, but they cause you grief. And this global namespace for recovery also causes you grief. And we have great plans to so the libraries are available open source, and some companies are using them already. The S group libraries Obviously, some of the other release stuff is in the virtual machine improvements are in the Erlang OTP download that everyone gets. But we'd like, in particular, to put this S-group technology into some larger scale frameworks for systematically building large Erlang systems. Thank you.